Welcome to the course on FPGA based signal processing systems. In continuation to the part we have done with the digital modeling, the circuit modeling, we have the structural modeling of combinational logics. So, combinational logic and the sequential logic, we look into them separately, each with the structural modeling and then data flow model as well as the uh, behavioral description. So, the combinational logic circuits are only depending on, or the output of the combinational circuit depends only on the current inputs. So, for example, if we take a block of gates, logic gates, there will be input and output. This circuit, that combinational logic circuit, there is an input and an output, which need not be only one, there can be multiple inputs as well and multiple outputs as well. So, n input and m outputs. So, this output or the outputs depends only on the current input given to the logic system. So, there won't be any past input storage involved in the combinational logic circuits. That means n, this particular instant input is only deciding the output, and no feedback loops. Similarly, the past output is fed to the fed as an input to the combination logics, no such things of no feedback loop. So, combination logic circuits are very simple with the logic gates, and especially these circuits would be the built-in gates or the multiplexers, decoders, encoders are few examples of the combination logic circuits. So, we look into the structural design elements the Verilog offers for combinational logic. So, the syntax of Verilog instance statements, I had known this already, the component name and then instance identifier, the expressions, the expression 1, 2, 3 required. So, this is like a component name and instance identifier expression. This is the first format, and the second format is component name and instant identifier, port name, dot port name expression. This is local expression we were calling, and port name and expression, port name and expression. So, instantiation of the module can be in two formats. So, the Verilog offers the built-in gates or the primitives as AND, OR, NAND, NOR, XOR, XNOR, buffer, NOT, get, buff if 0, buff if 1, not if 0, not if 1. So, all these primitives we are going to look into that, and how do we use them in our Verilog modules. So, these are built-in gates. Now, the primitive AND gate. So, the AND gate, you know, the how it is drawn, and the truth table for it is, you know, when it is 0 0, the 2 input AND gate gives you 0 0 1, output is 0 1 0, and output is 0 1 1, the output is 1. So, this much is familiar. When the inputs, because Verilog is 4 logic system. So, 4 value logic, in that case X and Z. So, the unknown and high impedance state also matter. So, when suppose the inputs are unknown, what would be the output? The input is high impedance state, what should be the output? So, we take this I2, for example, this 0 1 XZ. If I1 is 0, in that case what the table would be. So, this would be if this is 0, whatever may be I2, that's the output will be 0. So, if this I1 is 1, then it comes out to be that, because this is going to be, this is 0 and 1 1 1 1 1x, this is unknown. So, depends on this, the output will be, okay. So, if it is 0, then 1 and 0, this would be 0, 1 1, this will be 1. So, if the I2 is easy and this I1 is 1, again this high impedance state is an open circuit, okay, this is unknown. So, the output takes the value unknown, either it can be 0 or 1. So, considering this one is 1 and I2 is in high impedance state, okay, this high impedance state is open circuit, okay. So, this would, the output is unknown here, it doesn't drive into high impedance state. That should be kept in mind. Similarly, when the I1 is an unknown, okay, so depends on this. This can be, if it is unknown, then the don't care here, don't 0 or 1. So in that case, I2 is 0, then it depends on, this will be 0, 1, it is also x, x. So both the inputs are don't care, and this is also x, and is the x and z gives also again x. So the high impedance state, the I1 is given as high impedance state. Okay, for these combinations would also offer this, because the one input is definitely 0, so this is 0, whereas the other combinations it is going to be xxx. So similarly, it doesn't allow the output as high impedance state in any of the conditions in the primitive gates. So NAND gate, just quickly giving the truth table. So it should be for 0, again this is going to be 1, 1, 1, 1 irrespective of this, and 1 it is going to be, these two gives the xxx, and x, this is going to be again 1, these are unknown, they don't care, and z is 1, don't care. So no impedance, high impedance, both the inputs are high impedance, then also the output would be either 1 or 0. So it doesn't drive into the high impedance state. So the OR gate, similarly 0, 1 x z, if I fix this I2 as that, and 0, 1 x, and this is x. For 1, again all of them will be 1, because if it dominates irrespective of other input. If x depends on that, only 1 is dominated, other inputs are, for other cases it is don't care. So again here 1 will space 1, the remaining are don't care. Similarly for the NOR gate, quickly 0, 0, 1 x z, 1, 1, 0 xx. So in 1, 1 the NOR gate, this row would be 0, 0, 0. If both are don't care, and see that x and x0 xx, C would give you the unknown output or the don't care. So XOR gives the details of all other things, like this 0, 0, if both the inputs are same, it gives the 0, 0, 1, if two different inputs, then that is going to be 1, and 1 here, and this is 0. So this portion is known. So all other combinations, it would offer the don't care conditions. XNOR, similarly, that there is a NOT gate at the output. So we have the exchange 0, 0, 1, 1, this portion is a change, the remaining same as the XOR. In case of buffer, now the buffer, just it passes the input to the output, and so if it's 0, the output is 0, 1, the output is 1, and the X, the don't care, the output is also don't care, and Z, the high impedance state, the output is also don't care, it is not high impedance. In this case, it doesn't drive to or built-in gates, that is these gates doesn't drive into high impedance state. Not, that's a buffer, this is not gates, though the output is complemented, sorry, input is complemented at the output, 0 that is 1, and 1 it is going to be 0, don't care, again this is don't care, 0 it will be 1, 1 it will be 0, Z also, yeah, the high impedance state also will be don't care. So the gates, so we have seen so far, are not new, whereas only the logic values it takes, the four value logic system, X and Z should be if inputs, then it will drive to don't care, where it will drive to don't care needs to be known. So if buff if 0, so this is the tri-state buffer, which is active low, the control signal is active low. So when this control signal is 0, the input is passed to the output. If control signal is 1, it doesn't pass, this input is not passed to the output. So the state will be high impedance state, that is considering this as a buffer. which has a switch, the switch will be opened or closed depends on the control signal. Okay, so if control signal is 0, it will be closed, and if it is 1, and it will be open. So the truth table for this buffer if 0, that is it's a buffer. If 0, this input is passed to the output. So let's take this in buffer if 0 input and control, various combination of input and control. So the input is 0 and the control is 0. We said that input will be passed here, this is passed over here. When it is 1, that it is going to the high impedance state, irrespective of the input, whether it is 0 or 1, the gate output will be high impedance. And if the control is x, so x here, so it depends on either it is going to be 0 or 1, so it is specified as L. If it is 0, then the input will be passed over here at the output. If it is 1, it will not be passed, it will be in the high impedance state. So to specify these two states, L can take both 0, Z. So the 0 are high impedance state. Similarly for Z here, if control input is Z, that itself is high impedance state, the input is 0, input is 0, in that case it can take either the output as 0 or high impedance state as well. Okay, so there is a possibility of this is to be noticed L. And if buffer if 0 in the gate input is 1. Okay, so input is 1, you have 1, the control is 0, so 1 is passed directly, and if it is not, then high impedance state. If input is 1, the x is 1 or 0 depends on that, it is going to be whether it is going to be passed or it will be retained in the high impedance state, depends on x. So H is represented to specify, it can say H can take two values here, either 1 or Z. So high impedance state, or it can be 1. So H and L, low can be 0 Z, H can be 1 or Z. So control can be X, similarly input can also be X, either 1 or 0, depends on that. It is going to be at 1, when control is 1, this is going to be high impedance, otherwise whatever X is at the input will be passed. So again the input, it is in high impedance state. So what happens, even if this is 1, that will go to high impedance state, other cases it will be don't care only. So it is going to be don't care. So this is buffer if 0 gate truth table. So not if 0, so the buffer if 0 buffer with the control, here not if is, it's a not gate with the control, active low control. So the truth table again will be 0, 1, x. This control can take the 4 values, if value of any of this, not only 0 and 1, don't care, and high impedance states as well. So 1, 0, this is going to be an inverted input if this is active low, that's the only thing. Otherwise it can take, depends on x. If this is 0, either it can take 1 or Z. Similarly for 1, it can take L, XZ conditions. X, except this 1, other things will be don't care. So for Z also, this is don't care. So only changes were here, and the changes in the thing. So this is not if 0, but if 1. So just control input is 1, that would pass, the input is transferred to the output. If control input is 0, then it is going, output will be in high impedance state. So taking this in 0, 1, x, if this is 0, so will be high impedance state 0, and the control input is x, that is don't care, 0 or 1, it would be the input take L. One case goes for the high. This is, you can notice the high impedance state here at control 0, all of them will be high impedance state, and the remaining, so only this can take the two states, either 0 Z or H Z. Similarly, not if 1 is not, and if control input is 1, that this is complemented, input is complemented, otherwise it is high impedance state. So again, notice the HL and then states. which can take both two states, either 1 or z, or this one is 0 or z. High impedance states, when the input is 0, whatever may be these conditions, it will be high impedance state, and other things only don't care. So buff if 0, buff if 1, not if 0, not if 1 are the gates which consider the high impedance also in the output. Okay, so that is it is not only don't care, it can have 0, 1, don't care, as well as the high impedance state. So now instantiating this tri-state buffer with an example. So taking this 2 to 1 mux, that is to for simple example which we had used logic gates, simply the AND OR gates and NOT gates also. So the tri-state buffers now can be used for realizing this 2 to 1 mux. So the two inputs are x and y, and the select signal is given over here. This is buff if 0 and this is buff if 1. If you see that these control inputs are tied together to give the select input S, and the outputs are tied again to give F. So this F is driven by two of the outputs. So this is their multiple driver. So multiple driver signal, let us see in the Verilog code what is the difference we have to change, what is the declaration, how this F needs to be declared in the Verilog code. So other things, so 2 to 1 mux, module, N module, we have this 2 to 1 mux tri-state, it's a big module name, and the inputs are x, y and s, output is F. Okay. So declared input x, y, s and output F is so far good. So this x, y, this input and output can go here as well. Okay, so the declaration can be mentioned at the within the port with the port names as well, or the identifiers. And there is a tri F, we can see tri is a keyword again which is introduced in this when we use the tri-state buffer, which can go to the high impedance state, or it's the net which can be driven by multiple signals. So then that one should be declared as tri. So this can take high impedance state as well. So because a certain condition, if this in 0, this is only first gate will be active and the second will be disabled. If it is 1, and the second will be active and the first will be disabled. So in this case it should not be so here is, if we look at the instantiation. So this is used for mux, which can have one select line, 2 input x, y, and just giving this is F. So 0, 1. So if it is 0, so you can see the buff if 0 instantiation, that is the built-in gate. These are gate instantiation. There is only in the structural model, there is only 2 gates needs to be instantiated. Here the logic gates are available. So buff if 0, this is B1 is an optional component name identifier, instance identifier, and F is output. And if you recall that X should be the data input, okay, this should be specified. This order is important here, the order matters. F output in the built-in gates, when you instantiate it, output, data input, and then enable input. This S is enable input, so it should not be changed, the order should not be changed here. F, X and yes. So similarly buff F1, the second gate, this one, this is B1 and this is B2. Buff F1, so output is F again here. So the F is driven by both the gates, and Y is the input, data input, and S is the select line or the enable line here. So this is the code, and this F needs to be declared as tri, so to take the high impedance values. So that's the only change needs to be observed in the structural model of the tri-state buffer at 2 to 1 mux. So 4 to 1 mux, so we can expand that 2 to 1 mux with the tri-state buffer also, and just to give the few more details of the structural model, we have taken this example. There are 2 select lines. This 4 to 1 mux again can be viewed, the mux will be the select line, which is 2 bits, okay, 1, 2, 3 and 4 inputs. It can be I0, I1 which is I0, I1, I2 and I3. The output is out here. 0, 1, 2, 3. We mentioned the mux 4 to 1 mux. The select line is 2 bits. So S0 and S1, S1 and S0 together. So when this is 0, 0, I0 will be passed to output. When it is 0, 1, I think you know this mux function. So when it is 1, 0, it is going to be I2, output is I2, and 1, 1 output will take the I3 values. So now let's see the code of this instantiations. So mux 4 to 1 structural, I0, I1, I2, I3, S0, S1 are the select lines, and out. What are the inputs here? I0, I1, I2, I3, S0, S1. So these are inputs of 1 bit, and out is 1 bit. Also the declarations required here, this is wire and this is wire, and also Y0, Y1, Y2, Y3 are wires connecting the two elements, logic gates. Gate instantiations we have given here. The NOT gate, the first instantiation, not the output is S0 and the input is S0. Output is S0 N and input is S0. Similarly, gate 2, which has the output S1 N and input is S1. So this instantiations gate takes these 3 inputs, okay, and 1 output Y0. So Y0 3 input, I0, S1 N and S0 N. So next gate G4, output is Y1. These 3 are the inputs, and G5, Y2, I2, S1 and S0 0. So other gate G6, Y3 is output, and these 3 are the inputs. The multiple inputs, when you instantiate, the order does not matter, the input order does not matter, but the output should be called first. And G7 takes 4 inputs, Y0, Y1, Y2, Y3, and its out, this is output, this is OR gate. So all the gates are instantiated this N module. Now this is similar to the one which we had already learned. Now with this, in this example, we can also simplify this repetition of gate instantiations that we are going to see in the next example here. So this is for making it an array, then combining the signals with two of the wires can be combined into 2-bit vector and so on. This is again the 4-bit 4 to 1 multiplexer, which has 2 select lines, and the select line outputs are not S of 0, not S of 1. You can see the select line with this given in the square bracket 0, square bracket 1. So the first bit and the second bit of select line, and not S, the outputs of this is 0 and 1, the first and second bits of it. The G2, G3, G4, the gates, and then AND gates. Instead of having the 3 input gate AND gates in the previous slide, we have just made it with the 2 input AND gates. So the input is 4 inputs are I0, I1, I2, I3. So these are combined as one vector with 4 bits. The input I is combined as one vector with 4 inputs, that 4 bits. Similarly, the output of each G2, G3, G4, G5, D are named as D, which has 4 bits. The output of G6, G7, G8, G9, again the output N, which has 4 bits, and the output Y is 1 bit. And let us see how we have combined these 2 signals, also these 2 signals, the bits, and these 2 bits, and 4 bits of 1, 2, 3, 4, also the 4 bits of this 1, 2, 3, 4, and the output is Y. Also the input also has been combined as 4-bit input. So taking this module, mux 4 to 1, this S, I and Y. See, this S is a select line, and I the 4 inputs, the 4-bit input, sorry, and then Y is 1 bit. And what we are going to, how we are going to combine it. So when you say input, this input S is the select line, 2 inputs. Okay, so the 2 inputs are combined. You see, made it as a 1 vector. Okay, S is a vector 0 colon 1. So that means S naught and S1 signal are combined to have 2 bit S of 0 and S of 1, that is input. Okay, instead of having S0 and S1. So similarly, the other input I, the data input to the multiplexer I of 0, so here as combined as 0 to 3, 4 bits, 4 inputs, 4 single bit inputs are combined as one vector 0 to 3, I of 0, I of 1, I of 2, I of 3. So and output Y is so this is I is a 4 bit input vector I of 0, I of 3. So this is about input output declarations in the combinational logic. And now what are the wires needs to be declared? Okay, so the wires are the connecting G1 and G2, G0, G1 connecting G2, G3, G4, G5, and here G0 connecting G1, G2, G3, G4, G5. So this connection, that is not S again is combined as 2 bits, these 2 outputs of the NOT gate as wires 0, 1, 2 bits, and the other here D, there is one signal D and there is another signal N. So the signal, the wires connecting G2, G6, G3, G7, G4, G8, G5, G9 or D. So D is combined 0, 1, 2, 3 are combined as 4 bits. Also the N, the output of G6, G7, G8, G9 is going as input to the OR gate. Those are combined AND OR combinations as N. So you can use this variable as your choice, but these are the combination. How can be individual single bit inputs can be combined into multi-bit vectors. Okay, so this is what these are wire declarations. Now instantiation. How can we combine these instantiations as well? So there are 2 NOT gates. Okay, in this example, so the NOT instantiation, the gate instantiation starts here. NOT, the first gate G0, okay, and the second one G1. Okay, so G0, if you notice, that is the output is not S of 0, and input is S of 0. So instead of writing not S 0, you see the square bracket 0, that is representing the first bit of this. Okay, and S of 0, this input S of 0. So we have to specify this, need to include the square bracket which is giving the indexes. So G1, similarly not S of 1, and S of 1 is the input, the square brackets, this is the input and this is the output. And you can also notice this NOT gates are here there is no semicolon, not separately, not G0, there is this one instantiation, write this NOT and then G0 the first gate, comma, and then G1 the next gate, semicolon. So here your both the gate instantiation is completed. Instead of writing NOT, again not G0 in this NOT suffix S 0, comma S of 0, semicolon, again not G1 not suffix S1, comma S1, semicolon, instead of writing this way. So this can be avoided and this can be avoided with and put a comma. So all the NOT gates can be combined and instantiated. Similarly, all AND gates can be combined. So see the example again here, how all AND gates are combined in this instantiation. So G2, G3, G4 and then G5 or AND gates. So this takes output as D0, this D1, D of 1, D of 2, D of 3. So comma, the inputs are not S of 1 and not S of 0 first gate, and not S of 1 and S of 0 in the second gate, and 3 similarly, and 4. So you see the commas over here. So this is not complete, and you have also combined these instantiations G6, G7, G8 and G9. This is also an AND gate. So the AND is mentioned only once. Okay, all 8 AND gates are instantiated with a comma, and then the final gate, that is G9, N of 3 is the output and inputs are this D of 3 and I3. So, this DF3 and I3, and then put a semicolon if all the gates are mentioned here. These are instance name, that is optional anyway, G2, G3, G4, G5, G6. This is for clarity we included. Only one OR gate which takes 4 inputs, N of 0, N of 2, N of 3 and Y. So, in this example what we had done is single bit inputs are combined into S of 0, S of 1, here select lines, and I is input is combined 1, 2, 3. So, it is possible to combine all the select line and inputs also as 6 bits possible, and we have to correctly identify which one we are using it in this as inputs. Here in the declaration, in the instantiation, we have to mention that. That's the only thing. So, how to combine this multi-bit vector, single bit inputs and outputs as multi-bit vectors, how to combine the instantiation of AND gates or not gates. If you have multiple gates, it's not it need not be and all ANDs should be mentioned, only one AND comma separated instantiations will, and finally do not forget to put semicolon. This is only one OR gate, so OR gate is mentioned over here. So, this is to simplify the code again. Then we take the example of this 2 to 4 line decoder. In the 2 to 4 line decoder, so you have similarly 2 inputs, A0 and A1, and there is an enable. Okay, so I think you know the table, and output is D3, D2, D1 and D0, 2 inputs and 1 enable. Keep this enable for all combinations. 1, if enable is 0, then it will not give you any output here. So, this would be 0, 0, 0, 1, and here 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So, D0, D1, D2, D3 outputs should be. So, this is the truth table of our functional table of this combinational circuit. So, you have this A0 and A1 and its complements, the enable gate. So, it is two layer, like in the 4 to 1 marks we have 2 layer of gates. Again the AND NOT gate is the first one to level of this G0, first level, second level and third level gate structure. So, it can be combined and make it with also simplified things are available, just to show that the levels, different levels of gates as well. So, the 2 to 4 line decoder, it is a structural description again. The module give the decoder structural, Verilog and so on. The enable A0, A1, D0, D1, D2, D3. Inputs are 3, enable A0, A1 and enable also. Output D0, D1, D2, D3. Now, so wire declarations 1, 2 and 1, 2, 3, 4. So, all of them is going to be the wire declarations. Again combining this in inverters G0 and G1. G0 is that is having the G0 which is having A1N and A1 as the input, and G1 as A0N and A0. So, this is only one declaration of NOT gates with comma and semicolon. So, the other declarations, all AND gates G2, G3, G4, G5, G6, G7, G8 and G9, all of them, and it outputs N0, N1, N2, N3, and the G6 outputs are D0, D1, D2, D3. Here again this could have been combined. So, this inputs and the outputs D can be made 0 to 3. Similarly, N can be made as multi-bit vector as well. That is possible to have them, and similarly this A lines can also be 0 to 1, 2 bits can be made. So, I mean here is the select lines, and its output AN, I just give this AN 0, 1 can be declared. So all of them can be given as these are inputs, and enable is of course that is a single bit, 1 bit input. So these are inputs and these two are intermediate, D is output and N is the intermediate wire. So the gates, AND gates G2, G3, G4, G5 takes these 4 ones, and the G6 gates taking the enable as well as N0, enable N1 the next gate, enable N2 the other one, G9 enable N3. So the 4 D0, it would, when it is 0 0, D0 would be 1, and 0 1, D1 would be 1 0, D2, and 1 1, D3 would be giving 1. So the instantiations we have combined, and in this I have not shown the multi-bit vector. So it is possible we can make this as D of 0, D of 1, D of 2, and D of 3 as well. Similarly, N of 0 and N of 1, N of 2, and N of 3. So these points can be made this way to have combined multi-bit vector. So similarly, this output and select lines, like in the previous example, that 4 to 1 mux can be done. So with this, we have the structural model. The structural model, what we have done is what are the built-in gates available in the Verilog. So especially the buff if 0, buff if 1, not if 0, not if 1, how these tri-state buffers are used in multiplexers, and when it is driven by when the net is driven by multiple line signals, then you need to declare that net as a tri in the tri-state buffer, that because it can take the high impedance state as well. And how to combine the structural model, how to combine the instantiation of multiple gates, AND gates, or if you have multiple gates in the design, anyway we need to specify input and output for each gates, but the repetition of AND or the keyword component name can be avoided with the comma separated instantiations, and the final one should be the semicolon. So similarly, the 1-bit signals in the design can be combined as multi-bit signals and declared as multi-bit vectors, and then that can be used in the instantiation as well. So we will continue to have this few more design examples and then move on to the data flow modeling. Thank you.